welcome back. Work changes energy. This is really important. Today we're going to talk about the work energy theorem, and work equals force times the change in displacement.
They know all that already, don't they?
Yeah, and I just showed you guys. I put a force on the ball, over a distance, and what do we get?
You gave that ball energy.
We do. We give that ball energy, and in this case, we gave it
Well,
a
let's
specific
find out.
type of energy. Okay, moving
Yeah.
on here. All right. Positive work increases energy. Negative work decreases energy.
Well, now you did positive work because you increased the energy of the ball, and then when it crashed into that box over there, that box did negative work. It decreased the energy of the ball, didn't it?
So it's kind of conceptual,
Yeah.
right? Okay, let's go ahead and look at an example on page 248. Cash money flow, baby.
Cash money, cash money.
Okay, so say you only have a little bit of money, and
money.
naturally you want to get more money. You want to get some positive cash flows.
Positive cash flow.
So we get some more money, and then after that we've got this much money, right?
You got more money.
You got
get
more
that
money.
positive cash flow, you get that more money. Everybody like to have more money.
Then at this point, you've got more money.
Yeah.
Time to spend that money.
What's good is having more money if you can't spend it on something? Just
So-
sit around and look at it?
So here we've got a negative cash flow, and that decreases the amount of money we
Less
have.
money.
Yeah.
Less money.
It's just like work.
Yeah.
Positive work, more. Positive work gives me more work. It increases energy, and negative work decreases energy.
That's right.
Okay.
It's like money.
Where's my little clicker? It's over here. Mechanical energy, the form of energy due to the position, potential, or movement, kinetic, of a mass.
There's so many different kinds of energy. We got to narrow the field to just two things here.
Yeah, there's I mean, you got thermal energy. What else we got? Nuclear energy.
Electrical energy,
electrical
wind energy, blah, blah,
all
blah.
these
There's a
different
bunch
things.
of them.
We're just going to talk about mechanical energy, and the two types that we're going to focus on are potential and kinetic, but today's all about kinetic.
That's right.
Okay. So kinetic energy varies with mass and velocity. Write down this equation for me, please, if you haven't already. Let's get this right.
Yeah, if you had like a softball that you did that work on, it would have less mass going the same velocity, would have less kinetic energy.
Yeah, wouldn't have made that thing move so much, right?
That's right.
Okay. All right. More equations. Okay, let's talk about these relationships. So work changes, before we said that work changes energy, but today we're talking specifically about how work changes kinetic energy.
Yeah.
And how do we calculate the change in anything, the final minus the initial?
Yep.
Or you can use this equation too, the change in kinetic energy equals 1/2 times the change in the velocity squared.
Yep. When kinetic energy changes, it's the velocity that changes, not the mass.
Yeah, the mass doesn't matter, it's the velocity that's changing.
That's right.
Okay. Boom-ba-dum. Oh, an example problem. Miss Moore applies 45 newtons to a bowling ball, moving it through 12.5 meters. What is the delta K? Okay, well, first of all, we know that
1.2.
work equals the change in energy, and specifically the change in kinetic energy for today.
But what is work? That's force times displacement.
Work is force. Notice how there's lots of different definitions here? What was our force up there?
45 newtons, man.
Okay, so 45 newtons for my force. What was my displacement?
1.2 meters, man.
1.2 meters. That's going to give me my work. Let's plug it in. So 45 times 1.2. 45 times 1.2. And I get 54.
54
Ooh,
Newton meters or
54. Or joules.
joules.
Joules. Okay.
So that's the amount of work. Does that answer our question?
Oh, that does not answer our question. It says, what is the delta K? Well, it kind of does.
Yeah.
Work equals the kinetic energy. So if this is my work, then my kinetic energy, my change in kinetic energy is also 54 joules. They're the same thing.
And since, were you doing positive work or negative work on that bowling ball?
I was doing positive work on it. Okay, so now an 875 kilogram car is going that fast, how much kinetic energy does it have? So let's start off with a diagram.
Diagram's always a good idea.
Yeah. So, I don't want to use this color. I'm going to use graph. Okay, so it's 875 kilogram car. 875 kilogram car. And it's going 22 meters per second.
Yep.
How much kinetic energy does it have?
Well, what's that equation for kinetic energy?
Kinetic energy equals 1/2 mv squared. So 1/2 mass, 875, velocity, kilograms, 22 meters per second, and don't forget to square
Don't forget to square it.
That's what I always forget to do. Okay, so let's go ahead and do this. I'm gonna go 0.5 times 875 times 22 squared, and I get, well, that's a big number. I get, is that number right?
Yep.
Yeah, I'm right. 211750.
That's 211,750 joules.
Joules. Dang.
That's why cars are so dangerous. You get them going, they got a lot of energy.
Yeah.
They're
That's a lot.
dangerous. They're dangerous.
Okay, so what's my next slide say here? Same car speeds up to 44 meters per second. So we're speeding up. Okay, same car. Now I'll just call it my velocity meters per second. How much kinetic energy does it have now? Can't we just do the same thing?
Yeah.
Okay, so we'll say this is for
Everything's going to be the same. The mass is the same. The 1/2 is the same. It's just the velocity is different.
just the velocity. Kilograms times velocity, which was now
I
it's
notice
44.
it's going twice as fast. I wonder if it'll have twice as much energy.
That's a great question.
What do you think, boys and girls? Place your bets.
Make a guess. 0.5 times 875 times 44 squared. Are you right? Were you wrong? And we get 847
Dang, that's more than twice as much.
joules. In fact, that's 4 times as much.
Yep.
Why is that?
I think it has to do with the equation.
It's got to do with the square.
Yep.
Right? If it was 2v, it would be 2 times as fast, but it's a square, so whatever is there gets squared, so it's 4 times as fast.
Excellent idea.
Okay. So how much work was done to change the speed?
Well,
So this minus this?
work changes energy. That's the final minus the original, isn't it?
Work changes energy, so work is kinetic final minus kinetic initial. Oh, sorry, not equals, minus. Said the right thing, wrote the wrong thing. And we had, so 847,000 joules minus 211,750 joules. And so we get
Should be 600 something.
211,750. That's, yeah, you're right, 635,250.
Yeah.
Yep. Joules.
Joules, that's how much work, and that's positive
Yes, it
work.
is.
Yeah, that's
Yes,
positive.
because this is a positive, that's minus, we just do the math, that's a positive
Yes, ma'am.
number. Okay,
It has to be positive work because it increased energy going from 22 to 44
that is
meters
an
per second.
excellent point.
All right.
All right, what's next? Oh, let's go back. Okay, we are actually going to take a look. For your homework, you're going to do questions number 2 and
Yeah.
3.
We
but
need to
let's
show
do-
them number 1.
We're gonna do number 1 with you guys first. I'm gonna.
There's a problem we just did on the board, and that's on page 250. So if you didn't get this, you can just read this in the thing, and then it says, consider the compact car in the example problem.
Over here.
Okay, how much work is done slowing the car?
Oh,
You know what I want to say? We should turn this
you
off.
should. Get up there. Okay. So, how much work is done slowing the car down to 22 meters per second? So now
Got to put the brakes on.
the brakes are being put on. So, velocity 3 is 22 meters per second. And we got the same mass, right?
Yep.
So can't we just do the same equation here and compare?
Well, don't we already know how much kinetic energy it has?
We totally do. We've already done this math right here, right?
Yeah.
So our kinetic energy here is going to be 211,750 joules, but
What's the question?
what is the question? The question wants to know how much work is done. But it's slowing down, right? We're decreasing here.
No, it's going to be final minus original. We got a new original. The original is 44, and the final's 22.
So let's go ahead and take this number. Wait, the original is, final right here. So my change in kinetic energy here is going to be my final minus my initial. Okay, this one minus this one. Let's say this. My final was 211,750 joules minus 847,000 joules. And we are going to get...
We'll get a negative number.
We're going to get negative this number, right?
Yeah. Oh,
Yeah.
yeah.
Negative 635,250 joules. Put it in
Boys
your
and
calculator.
girls, do you understand what just happened? Going from 22 to 44, it had to be
Positive.
positive 635,000 joules. So we're going from 44 to 22. It's got to be negative 635.
And it's the same amount of work, but we just got positive and negative, cash money flow, or energy.
What's the next question? I think it comes to a stop, doesn't it?
Yeah, how much work is bringing it to a stop? So here we go. Okay, so now our fourth velocity is going to be 0 meters per second, and our mass is still 875.
I don't think we're going to need to do kinetic energy. The kinetic energy is going to be zero,
It's going
right?
to be 0. Yeah, it's not moving, right?
And they want to know how much work.
So if they want to know how much work,
And work changes energy,
if we figure out what the change in kinetic energy is, we know what the work is, right?
That's right.
And our final, we can just do final minus initial again. Here's the final one, right?
0,
Minus the initial one, which is
211. I don't think you're going to need a calculator for this one, Ms. Mo.
me neither. 750 joules. That is just a negative 211,750 joules.
This stuff is simple.
Yep. Just gotta get your sketch right. You know what I mean?
Yep.
To really understand what's going on. And it makes sense that it's negative. It's slowing down here. Okay. Anything else for that one?
I think that's enough for that one. Now we've got 2 homework assignments for them. They should get their book and read them.
Take a look at them while I erase.
I don't know if you can read that or not. We're on page 251. And number 2, a rifle can shoot a 4.20 kilogram bullet that's 0.0042 kilograms. So it says 42 grams. You got to convert that to kilograms. 0.0042. Look, I just helped you out. At a speed of 965 meters per second. A says draw work energy bar graphs. The hell with that. Let's start with B, and then C, and D, and E.
Hello.
You guys are going to do the work, and we are going to make a diagram.
Okay, let me refresh myself. So a rifle can shoot a 0.0042 kilogram bullet at a speed of that.
So
Okay,
it
so
starts off at
here's my rifle. Okay. And the bullet is, should I label it? I'll label this for them because I don't want them to have to convert it.
0.0042.
Okay. A rifle can shoot that much bullet at a speed of 965 meters per second.
So the velocity final is 965 meters per second. Can we pause this a moment?
Yeah,
Hi, Mark. How you doing?
Good morning.
we can pause.
All right. Where were we before we were so rudely interrupted?
Not really. He's the guy fixing our heater, hopefully. Well, kind of, sort of. Okay, so it is a shot out at 965 meters per second. Part B, 2B, says find the kinetic energy of the bullet as it leaves the rifle.
Okay, so they can do that. You've got a diagram, all right,
So for A, it wants to know the kinetic energy.
as it leaves the rifle. And then B wants what?
Or
B wants that.
B, C. Okay, C says, what work is done on the bullet if it starts from rest?
Yeah. You
Okay.
should be able to answer that one.
So right here, right?
Yeah. So the original velocity is 0. Yeah.
In that case,
Yeah.
okay, so burr, 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 burr. And then letter D says, if work is done over a distance of 0.75 meters,
That means
Right
the
here.
length of the barrel.
what is the average force on the bullet? Well, what's that equation for force?
They should have it in their notes if they don't have it memorized. They
Figure
just
out
solve,
what that is.
solve for force.
Okay, that's E. And then let's go ahead and go to E. If the bullet comes to rest by penetrating 0.015 meters into a metal, okay, so it goes like this, whoosh, whoosh, boom, boom, and it goes 0.015 meters. Is that right? That number?
Yep.
Yeah, into a metal. What is the magnitude and direction of the force the metal exerts?
Well, the metal's got to do work, and work is equal to the change in kinetic energy, so they should be able to take it from there. What's the final velocity here?
0,
The final is 0.
right?
So you should be able to do that one.
Okay, I think you guys got this. And then you're gonna do number 3. That one talks about a comet with a mass of a scary-looking number. It's just scientific notation. Don't worry. Okay. And it strikes the Earth at that speed. And they're gonna do A and B for that one.
All right.
Okay.
That's homework.
Go ahead and begin.
Bye.